Okay, so our first session today is on earthquakes and tectonics. So this session is going to be focusing on new research focused on fault characterization, earthquake ground motions, estimates of vertical land movement, and landslide hazards. And our first speaker today is going to be Harold Tobin. And Harold, you should have control over my slides, but there might be a little bit of a lag as you progress.
I'm going to jump in and say I will give you a 30-second warning as as Erin mentioned, when you have 30 seconds left. But for speakers, if you want to set your own timers as you go to keep track of that as well, that might help you keep on task.
All right, thanks. Hopefully you can hear me. It looks like I can change the slides. Thanks, Erin. Yeah, good morning, everybody. So the first step in understanding our earthquake and tsunami hazards is really identifying the sources of those hazards, which is fundamentally from faults either on or offshore. So the first team that we'll discuss is the one that's looking at doing a better job of characterizing what those offshore faults with rupture potential are. And that's a group of us here at UW, myself, Madeline Lucas, and Anna Ledexi, as well as our collaborators down at the USGS in Santa Cruz, Janet Watt, and actually others besides Janet as well. So, we all understand that there is, let's see, changing slides, there we go. We all understand that there is the potential for a megathrust earthquake on the Cascadia subduction zone that could generate tsunami and strong ground shaking. And a lot of the modeling that's been done really treats that as sort of this sort of fairly fundamental fault zone, the megathrust itself. But in fact, the details of how that kind of slip occurs that could generate those hazards really comes from the detailed geometry of the megathrust itself, as well as the faults that branch off of it and come to the surface, which are known as splay faults, potentially, and parameters of earthquake slip like how far up the fault the rupture actually comes before it stops, whether it goes all the way to the surface at the seafloor, or whether it stops somewhere at depth along the thrust fault, how far back along the fault rupture goes, and so on. So a lot of that is really still characterized only in fairly sort of broad brush ways. And so what we're doing now is using a wealth of new and also legacy offshore data, including detailed bathymetric mapping that's getting better and better as time goes by, and new geophysical data, specifically seismic reflection profiles that help us to characterize the active faults that have either evidence of past slip to the surface that's relatively recent, which means that they might be candidates for future slip in future earthquakes. And then we're basically doing that work so that the teams that are doing modeling, the three-dimensional modeling of earthquake and tsunami simulations, can use these kinds of structures in new scenarios that you're going to hear about from other folks in a few minutes. And the big challenge is just that it's actually quite complicated offshore. It's not like the cartoons with a simple single planar megathrust, and we don't know really what's more or less likely to slip in future events. So just some examples of what that looks like. One big piece of it that UW PhD student Maddie Lucas is working on is new seismic reflection data collected along all these track lines in 2021 on a 40-day survey of the Langseth vessel. All of these are deep penetration seismic reflection lines. There's an example of one that's shown in red there off of the Grays Harbor region over here. And you can maybe just barely see, given the quality of screen, that there are a number of these splay faults that branch off of that. An interpretation down below, including potentially a substantial or a sort of first order major boundary splay fault system, and many others actually in the offshore. So mapping out and understanding what those geometries are is the ongoing work that Maddie in particular is doing right now, along with a number of different collaborators. We can really look at these offshore structures at a variety of different scales of resolution. And so that deep penetration seismic reflection work is one part of that, but so is the high resolution bathymetry, and so is a bunch of new seismic reflection data like this, what we call Sparker profiles, which I'll show you another example of in just a second, and give us more information. So here's another map with even more track lines of various kinds of surveys. The area that's shown, that's kind of colored in there, is what we call the landward vergence zone, but that's really a stand-in or a proxy for the portion of the Cascadia subduction zone that's seen as having the strongest locking, which means the strongest potential for the largest slip in future events over large areas. And that really encompasses the offshore Washington to northern Oregon region, as you can see, and specifically offshore in our collaboratory areas, the Toclin to Taholah and Astoria to Newport regions. So we're using all these newly processed lines, mapping out the faults, building 3D geometric models of those faults, and then analyzing evidence for that recency of fault activity. I keep trying to, oh, there we go, it does work that way. Looking at a little more detail, here's another section with a line shown over here. This is now one of these Sparker profiles, and this is a slide from Janet Watt's team at the USGS. We're all working
30
together.
seconds.
Thank you. With Anna Ledexi working on this in particular here at UW. And this is just the upper few hundred meters of the subsurface. And you can just see that some of these structures look like they've grown in the past, but are maybe not growing today. And others have faults that come right to the surface. So that's all input for our understanding of what's actually active out there. And even at higher resolution details in the bathymetry, what kind of scarps and other evidence of surface rupture that's quite recent could be formed. So again, building 3D fault models is the goal, using these results to define plausible rupture and seafloor displacement scenarios, and then working with the teams you're about to hear from to guide and prioritize their efforts. And ultimately, it links to onshore, working with people who are looking at the onshore evidence for larger and less displacement, for example, in different places, or variable coastal evidence for past events, and tying that to our offshore faults and features. So when we think about what questions we have, it's really what are some of the scenarios that might be of particular interest to you as various agencies and stakeholders in this kind of effort. And with that, I think I'm done.
All right, so our next speaker is going to be David Schmidt from University of Washington. And David, you should have control over the slides.
Great, thanks, Erin. So good morning, everybody. My name is David Schmidt, coming to you from the University of Washington. I'm representing the team on the COPES hub that's focused on characterizing the vertical motion of the land and exploring the consequences for climate change, tsunamis, and coastal ecology. So the coastline delineates the interface between the level of the ocean and the land, and the communities along the coastline are put at risk when this boundary changes, for example, due to sea level rise. So predicting the changes in the coastline requires an understanding of not only the sea level, but also the vertical movement of the land from things like earthquakes or other geological processes. This photo on the right kind of demonstrates how the level of the land can change through time. And as you can see, there are multiple marine terraces that are marked on that figure, which represent old ancient shorelines. And this is just a reminder that the land is not static through time, it's a dynamic quantity that moves up and down. So our team will provide predictions on the vertical movement of the land over the next century. And the motivation for this work is really to provide stakeholders with improved estimates of the vertical movement of the land so that they can better assess the risks for climate change, tsunamis, flooding, and the ecology of estuaries given changes in base level. For example, a large megathrust earthquake is going to cause the ground to subside by a meter or two, and that will put communities at greater risk for flooding from climate change and tsunamis. So our oops, went too far there. Okay. There we go. So our research goal is to provide stakeholders with a site-specific estimate of the vertical land movement for a range of possible scenarios. In other words, to provide a probabilistic prediction of how the land level will change through time. So we're developing a range of products with this. And here you see kind of a listing of those products. And we've already started work on a map with the current vertical movement of the land by ingesting a range of data sources such as GNSS, INSAR, and leveling data. And we're using a model to help interpolate where observations are sparse. And so you can see an example of that product on the far right, where we have uplift along the coastline. We've already completed this for Washington State, and that's published in this paper by Newton in 2021. And we're currently in the process of extending this down to Oregon and Northern California. So in the end, we're going to have a product that covers and spans the entire Cascadia coastline. In future work, we plan to model the change in elevation for a wide range of earthquake scenarios and post-seismic processes. Using a logic tree like Aaron showed in the previous slide, we can then assign a probability to these different outcomes. So let's see here. So there's a cartoon here on the lower left. And what that cartoon depicts is what a product might look like that we hope to produce. We can ask, what might the land do in the town of Westport in the year 2050? And that could be used for some planning horizon. If there's no earthquake in that period of time, then we can expect the land to slowly uplift on the order of a few centimeters, which would effectively offset any rise in sea level. However, if there's an M9 earthquake offshore, then the coastline would subside by 1 to 2 meters. And the magnitude of the subsidence would depend on where the offshore earthquake is located. So this scenario would have a dramatically different consequence for coastal communities, as it would increase the degree of coastal flooding, among other consequences that they might want to consider. So our hope is that community planners could use a product like this to help in their decision-making. For example, a community might set a threshold for when a critical piece of infrastructure needs to be relocated if the probability of significant subsidence crosses some threshold, some probability threshold. All right, so our work here is still in progress, and we're still formulating our research plan. We are looking for feedback to help guide this work, and so we have some requested questions there. First off, we're interested on how state agency and our stakeholders might utilize this product of land movement through time. We're interested to know what resolution is helpful. Do people want to have this product down to individual city blocks, or is 10-kilometer resolution sufficient, or regional resolution like 100 kilometers sufficient? We're also interested on how to disseminate this product, how people want to receive this information. Do you just want tables of data by location? Do you want it delivered to you as GIS layers, or just PowerPoint figures for different communities that you can then just bring and go to what's of most interest for your particular needs? So I'll stop there, and we look forward to hearing your feedback.
Great, thank you, David. Okay, so now we're going to move on to our next speaker, Allison Duvall from the University of Washington. Allison, you should have control over my slides, but be warned, there's a little bit of a lag. So you can go ahead.
Okay, thanks. Yeah, I just was playing with it and it seems to be working. Good morning, everyone. As Aaron said, I'm Allison Duvall from the University of Washington, and it's a real pleasure to be taking part in this workshop with all of you today. So I'm representing a collection of individuals as part of Team 1 COPES who are interested in understanding past and future landslides in coastal Cascadia, as well as their connection to other hazards and longer-term landscape evolution. And we're, of course, motivated by the fact that landslides are a common and often destructive agent of hazard and erosion in our region. So we have 3 major research objectives as part of our landslides team, and I've listed those over here as 1, 2, and 3. But I thought it might be most illustrative to also show you on a map where it is that we're focusing each of these endeavors, at least at present time. So one of our major objectives is trying to quantify both the timing and spatial location of past Cascadia landslides. And so you can see from the purple shapes on this map that many of the places that we're presently or near to be focusing on are adjacent to or overlapping with the Cascadia COPES collaboratory community sites. But I also want to make sure to note that this work is more regional in scope than any one single community. We're also interested in considering the geomorphic or hazard cascade from landslides, as well as their impact in longer-term landscape evolution. And much of that work is right now focused on trying to forecast where landslide dams on local rivers might end up. And that work presently is focused mainly in Oregon. And then we're also interested in forecasting future landslide hazard and risk. And right now, we're focusing on the communities of the greater Seattle region and the Tokeland to Tuchola region of Washington state. So I thought I would just spend a moment or two trying to give a few more details about each of these objectives. And I thought I would use UW graduate student Eric Herzig's recent work combining landslide mapping, landslide dating, geomorphology, and earthquake simulations on the Seattle fault to try and understand which of the many deep-seated landslides in Seattle may be related to co-seismic drivers. And this work is only possible when we have both maps of past landslides and some information on their timing. So this is why we're really motivated to try and extend what we know about the timing of past landslides. For our second research objective, much of that work is being led by UW graduate student Paul Morgan, who is presently working to create maps of likely landslide dam susceptibility. As I mentioned, right now, that work is being focused on the Oregon Coast Range, and we're starting there because of the excellent existing landslide inventories, as well as landslide dam inventories, and really good coverage of LIDAR. Paul is also working right now to seed some future work using landscape evolution models to think about how landslides and rivers interact to shape the longer-term topography in Cascadia. And for the third objective, forecasting landslide hazard and risk, this work is being led by UW graduate students Daniel Acosta, as well as Eric Herzig, who are using some foundational work by Alex Grant, Will Pollock, and Joe Wortman that allows us to combine landslide models with earthquake simulations in order to develop scenario or probabilistic co-seismic landslide inventories from those earthquake simulations. So I'm describing a range of products here that we're expecting, including dated landslide inventories, high probability landslide dam models, or maps, model simulations, and some other geomorphic measurements, as well as probabilistic co-seismic landslide inventory forecasts. I've showed you where our priorities are right now and in maybe the next year or so, but we do intend to expand that out to more of the region. And so it's really important that we check in with everyone today and in the future to ask questions like, how can our work complement your ongoing initiatives, which we know there are many related to landslides up and down the coast? And are you interested in any of our maps or data products? And could these be slotted into the present state or federal databases that we know are maintained on landslides? So we're looking forward to those future conversations. Thanks very much.
Great, thank you, Allison. So again, we're going to take a minute to go over to the Miro board. If you don't already have it open, the link is in the chat, and we'll take about a minute to provide any feedback to Allison.